Hello, my name is Anuj Soni, and I want to welcome you to my first video on malware analysis topics. Now, my goal here is to produce small, bite-sized videos that you can hopefully learn a couple things from while you're eating your lunch or taking a break from other work. I do want to say up front that this video will include multiple edits because my intention is to remove any pointless ramblings on my part or noises I can't control like babies crying. And this is all in the spirit of simply producing the most concise video possible. For that reason, I may also speed things up if the processing at any one point is simply taking too long. But with all that said, let me go ahead and get started. Now, the focus of today's video will be demonstrating a potential workflow you might use for performing code analysis with Ghidra. The sample we'll be analyzing is WannaCry, and I chose WannaCry because it's a type of malware many people are already familiar with, and the purpose of this post is more to discuss how to use Ghidra to perform code analysis and less about the actual malware sample. Now for the analysis today, I'm using my standard Windows 10 64-bit OS in VMware Fusion. I have a sample here of WannaCry. I'll include a link to this sample in the notes for this video. I've also downloaded Ghidra version 0.9.4. And so I have the bat file that's going to be used to actually launch that. And now I'm going to go ahead and double click on this to actually open up Ghidra. All right, I'm going to go ahead and close that tip of the day for now. And now I have my projects window for Ghidra. I'm going to go ahead and open up a new project by going to File, New Project. Two basic options here are non-shared versus a shared project. Now, in the case that you are performing reverse engineering in a collaborative environment, you'd certainly want to explore this shared project feature, which is pretty nice. But for this video, I'm just going to choose a non-shared project for individual analysis here. I have a standard project directory. You'll see a reference to rem, and the reason you're seeing that is because this VM is based off of the Windows rem workstation we use in the SANS 4610 reverse engineering malware course. And so in that class, this is the standard username. I'm now going to include a project here, and I'm just going to call this WannaCry. Press finish. And now that I've created the WannaCry project, I can drag and drop the actual file into the project. It's going to start importing it here. I'm going to press OK. And now, as this progress continues, you'll start to see references to it loading imports, loading specific DLLs associated with those dependencies, and so on. Okay, once it's done doing its initial processing, we got a nice imports result summary here. And you'll notice this is a 32-bit application. It is a Windows application. And it's got a bunch of other data here as well, including its version information. Okay, but for now, I'm just going to go ahead and click OK here. In order to dive into this sample, I'm now going to double click on it. Oh, got to watch out for that dragon. All right, now Ghidra is telling you that it has not actually yet analyzed the sample. So despite all of the processing that's taken place so far, it hasn't really done a deep dive into this file just yet. So in order to do that, I'm going to go ahead and click yes. I would like to analyze this sample. Now, generally, you can accept the defaults, but there are two changes I like to make here on the left-hand side under analyzers. Specifically, I'm going to check this decompiler parameter ID, because we are going to want to take advantage of the decompiler output, and to the extent possible, I'd like Ghidra to identify any parameters being passed to functions. And then on a similar note, scrolling down, you'll see an option here that specifies it can propagate external parameters. And again, this is so that I get greater visibility into functions that are being called. With those two selections made, I'm going to go ahead and press Analyze. And on the bottom right, you'll see the progress taking place. Now, you can begin performing some work while the processing is occurring, but I'm going to pause here and just wait for this to complete. Okay, so our processing is complete. We got this auto analysis summary, which includes a reference to a warning / error about incomplete PDB information. That's fine. We're going to press OK here. And now we have our main interface for navigating the code associated with this sample. I'm going to go ahead and maximize my window. And lots of different types of information here. Of course, the most important of them all is what we have in the center, which is called the listing window, which actually includes the disassembly. I'll talk about the other ones as they come up. Now, for some, this might be sufficient in terms of an interface and what this looks like. I do like to make a few tweaks here, and so let me show you how to do that if you prefer to do so. I'm going to go to Edit, Tool Options, and first I'm going to click on Listing Display. Clicking on Listing Display shows me options associated with the colors that are shown, as well as the size and the font. The only thing I'm going to change here is just make the font a little bigger to 14, and I'm going to make the text bold. Okay. Now going on the left-hand side to the individual listing fields, I can target a lot more granular configuration settings, and I'm just going to touch on a few of these. For starters, I'm going to click on the bytes field here, and I'm going to indicate that the maximum lines to display is 1, and this is just so I don't have numerous lines of opcodes. Okay, if I want to come back here to take a closer look at the opcodes, I can obviously modify this later. I'm also going to click on cursor text highlighting, and I like cursor text highlighting because, similar to other disassemblers, if I click on a register here, I want it to show me other references to that same register. While the mouse button to activate is defaulted to middle, I'm going to make this left, as that's the click I'm generally going to be performing here. Moving on to EOL comments field, I do like to see comments at the end of the assembly line if they are available. The change I'm going to make here is to show semicolon at start of each line, which is simply to kind of bring this view more like ones I'm used to seeing from other disassemblers that will not be named here. And I think that's all I'm going to change here. Oh, actually one more. Under the operands field, I'm going to choose add space after separator. Okay, and this is again just to make things a little bit more readable. So after making those changes and pressing OK, this is now my current view, which personally I think is an easier way to look at the actual assembly. Now you'll notice that it brought me to the MZ header here, which you may or may not like, but it's kind of nice because if I want to take a closer look at the actual PE header, then this is one way to do so. So let's begin taking a closer look at the actual code in this program, and there are multiple approaches to pivoting into code for this sort of analysis. One common approach is to begin with the import address table, find references to APIs defined there, and then look at the surrounding code to those call references. So let's go ahead and follow this approach. I'm going to choose Window here from the menu, and you'll see many different options here you might want to explore at one point or another. This is a good opportunity to mention the great help that is built into Ghidra. For example, symbol references are what we're going to choose next here, and if you want to get a quick description on what really that means, you can hit F1 on your keyboard while having symbol references selected, and it will pop up the Ghidra help, and it will specifically bring you right to the section that corresponds with the information you want to actually read about. So that's pretty nice. But let's go ahead and go back to Windows, Symbol References, and we're going to use this view to take a look at the imported functionality. Now I want to say that this does include much more than simply the IAT, but if you want to focus on imports, what you can do is sort by source, and if I click twice here, now I have only the IAT entries. Now, lots of different APIs I could focus on. For now, I'm going to take a look at this group of APIs here that have the word resource in them. And you may have seen some of these APIs before, but APIs like size of resource, lock resource, load resource are all associated with interacting with the resource section of the PE file. And that's often done because the resource section is a great location to store additional data or executable content. To take a look at a specific API, let's go ahead and just choose Load Resource. You single click on it on the left-hand side. On the right-hand side, you'll see the references. Now I'm interested in looking at calls to this API. So the access I want is a call. I'm going to single click on that entry. And in the background, you might have noticed the listing display actually updates and takes me to that location in the assembly. Okay, now if you mouse over the API, it's going to take you to what it's pointing to, which is basically the IAT, and that's what you see here. But if I mouse away, then that disappears. Now, looking at the actual instructions here, you see multiple calls. If I left click on one of these calls, it should highlight the other calls. That's part of the configuration that I changed up front. Above these calls, you see multiple pushes that correlate with the arguments being passed to this function. And in the auto-generated comments here on the right-hand side, you'll see references to the actual parameters that are being specified. Now, if you want to see a graph view of this function, we can go to Window and go to Function Graph. And here you'll see a breakdown of the individual code blocks and then the actual decision points associated with these code blocks. Now, if you want to zoom in on one of these, you'll start to see, similar to other disassemblers, you have the actual decision points associated with each of these code blocks. You have red and green arrows indicating whether or not the condition has been met and what code block gets executed after that point. It's pretty common to see these decision points, particularly after calls to functions, because they're often going to be evaluating whether or not the function executed successfully. So for example, here we see a call to a function in kernel 32. Now, notice we can't see the rest of this here. If you want to modify, whether it's in the listing display or in the function graph, if you want to change the way this layout looks, you can go up here, press this icon for the individual fields. And this gives you an opportunity to, for example, expand out or leave some more white space any of these columns. Now, in particular, right now, I can't see what it's pointing to within kernel32.dll, which import, and so I can expand this out as follows. And now, after pressing OK, I can see that this one is actually calling find resource, evaluating EAX, which is going to store the return value, and then based on the successful execution of that API, actually go one way or the other. Now, if I want to get back to my listing view, I can just go ahead and close this window right here and continue my analysis. Now, another way to get a different perspective on this function and the calls that are being made at a higher level is to go back to Window here, and now I'm going to choose Function Call Graph. Now, the call graph here simply shows the functions that are called by the function that I'm currently in. And taking a look at these APIs that are being called from this function, I can in fact tell that the resource is being loaded, accessed, and then perhaps something is being done with it. Now, what's being done with it is not exactly clear. Commonly, when malware accesses the resource, it's oftentimes to drop a file down to disk, perhaps, for further execution. I'm not seeing anything like that happening here. But I do see a reference to getProc address, and I know that getProc address can be used to resolve APIs at runtime, and so this might be worth investigating a little further. To do so, I'm going to go ahead and close the function call graph, and I'm now going to take advantage of the decompiler on the right-hand side. Now, we could certainly perform similar analysis as I'm about to using the disassembly on the left-hand side, but certainly the decompiler speeds things up, so why not take advantage of it? And after all, this was one of the most discussed, highly anticipated features of Ghidra. So looking at the top here, I can see multiple references to getProc address. And you might notice that when I click on the right-hand side, it actually updates the view on the left-hand side, and that'll happen if I click on the left-hand side too. It'll update what's on the right-hand side, generally speaking. So what's going on here? Well, as I mentioned, getProc address can be used to resolve the address of functions at runtime, and it looks like that's what's happening here, because in the arguments, I see multiple strings that are associated with well-documented Windows APIs. I got create process here, which is certainly used to actually spawn a process, and write file, for example, which can be used to write a file down to disk. So it looks like we are loading the resource, and we probably are going to actually drop this down to disk and execute it. Now, to build some clarity around that, I can start redefining a few things here. So for example, the return of getProc address is going to be, in this case, the address of create process A. So I'm actually going to modify on the left-hand side here. I'm going to right-click and basically rename this global and just call that create process A. And I could do this for all of them, but for now I'm just going to do it for a couple of them. I'm going to right-click here as well and do a rename global and call this write file. It takes a second to update, but you'll notice that it does update on the left-hand side as well. So when I highlight this, write file, and I start scrolling down, I'm trying to see when it's actually called, and it looks like it's called down here. Okay, and it is called after references to find resource, load resource, lock resource, and size of resource. So again, this should build my confidence that it is going to actually write this file down to disk, whatever it's getting from the resource section, and then later on, if I continue scrolling down, it will probably actually execute it, and that's what it appears to be doing down here. So now that we've determined that this function is loading a resource and then probably writing it down to disk for execution, it makes sense that this resource section might actually have a Windows executable in it. Well, one way to get visibility into that within Ghidra is on the top left here under the Program Trees window, and you'll see reference to all of these sections in this PE file. The resource is what we're interested in now, so I can click on Resource. That'll update the listing display here and actually give me some visibility into that section. Now if I start scrolling down, what you'll see very quickly is a reference to 4D5A, which you may be familiar with is the MZ header. And so I can go ahead and expand this out, and what I would find is that these bytes are in fact associated with a Windows executable, which makes a lot of sense given the API's calls that we just went over. So in Ghidra, what you can do is you can basically highlight all of these bytes as I just did, right-click, and towards the end here, you'll see a extract and import option. If you click on that, it'll actually identify it as a portable executable. You can press OK, and now it's importing a file into this overall project that we've created for WannaCry. And that's a key benefit of Ghidra, is that it takes a much more project-oriented focus to reverse engineering versus simply looking at individual files. And now this PE file in the resource section is going to be a part of my project, and I can perform auto analysis against this as well, just like I did for the initial executable. So I could click yes on this, choose the same options that I did before, and then give this some time to actually finish processing. Okay, so that's done processing. I'm going to go ahead and press OK. Notice we got that same warning/error. No big deal there. Now, the current tab that's open is associated with the resource. I'm now going to go back to my original executable here by clicking on the appropriate tab. I'm going to click this back button now to go back to the function that I was previously looking at. And now after a few clicks, I am back at the same function we were originally analyzing, the function that called find resource, load resource, and the other APIs. Now at this point, it makes sense, since I understand what this function is likely doing, to go ahead and rename this function. So I'm going to scroll back to the top here. I'm going to highlight this fun underscore name, which isn't very meaningful to me. I'm going to right click, and I'm going to go to edit label. I'm going to call this drop and run PE and press OK. And once I've gone ahead and renamed that function, it makes sense to see where this function is referenced. So I can do that by right-clicking, going to References, and Show References to Drop and Run PE. Looks like there's only one reference. I'm going to go ahead and just highlight this, and that takes me to the function that calls drop and run PE. Now you'll notice the function where we currently reside basically has two calls in it. One is to drop and run PE, and the other is to this other function. Now, one way to get visibility into what that other function might be doing is to take advantage of the function graph that we looked at before. So I'm going to go back to Window, and I'm going to choose function call graph here. And we can see the function where we reside and the other two. What I can do then is actually expand out these additional functions. So if I mouse over, this plus symbol shows up. If I click on that, I can see that this next function actually calls OpenSC Manager, create service, and then start service. And then of course my drop and run PE calls those APIs that I'm already aware of. Okay, but this is a great way to get a high-level overview of functions that call other functions, and we can see pretty immediately that this other function we haven't yet dove into is simply one that is going to create and start a service. Now, another way to get visibility into this additional function allows me to show some of the scripting capabilities within Ghidra. And for now, we're just going to take advantage of some of the ones that come built in. So to access the script manager, I'm going to go ahead and click on this play button up here, which displays the script manager. Now, Ghidra already comes with, as you can see up top here, 238 scripts ready for your use and modification. These are also all all can serve as great templates for scripts you might choose to create on your own. But for now, let me scroll down here and choose the section on strings. Okay. Now there's one Python script here called Recursive String Finder, which will basically recurse into the functions that are called from the functions where you currently reside and show you what strings are being referenced. And this is yet another great way to understand at a high level what these functions might be capable of doing, rather than double-clicking on each one and then backing out and doing that over and over again. So if I just double-click on this function here, you'll see on the bottom that it actually starts running in the console. So this might take a few seconds here to run, so we'll pause for a moment. And now at the bottom, we do actually have some output. Now taking a look at this output, now what it shows you is that within the first function at 407C40, which is the one we don't know a whole lot about yet, it is able to find strings referring to this format string, Microsoft Security Center service, and then what looks like perhaps the name of a service. And then we of course have our drop and run PE here, and has identified the following strings, some of which we've already talked about. Okay, so there's a good chance, based upon the call graph we saw earlier, as well as the strings associated with this function at 407C40, that it probably creates and launches a service. Okay, so we could, for the moment, decide to go ahead and label this one as well, something a little bit more meaningful. Now, you may have noticed that the shortcut to do that is a L. Okay, but for now, I'm just going to use the context menu, and I'm going to call this create and run, or maybe start rather, service. Press OK, and now I have both of those functions renamed. Now, I should mention that while we started by pivoting from the import address table, you can also pivot from strings, which is another common approach to identifying interesting blocks of code. To do that, you can go to Window and then choose Defined Strings. This will, on the right-hand side here, show you all of the strings that were identified in this program. And similar to the IAT, you can click on any of these individually, identify the references, and then dig into the code. So I hope you enjoyed this brief introduction to performing code analysis with Ghidra. Do subscribe if you're interested in seeing other videos that I post in the future. If you have thoughts on topics you'd want me to cover, please also include those in the comments below. And finally, if you're interested in taking the SANS 4610 Reverse Engineering Malware course, please go to learnrem.com to see the course schedule, and we hope to see you at a class coming up soon. All right, take care and have a great day.